Welcome to electronics, and the things you learn throughout your career in electronics can be applied across so many facets of electronics. So what you learn here, you'll carry with you and build upon for a long time. Now, I'm going to just kind of briefly give you an intro. There are electronics technicians. That's what you're going for. There are engineers. Engineers are usually considered at a higher level than a technician. Although there is some practical application, I think, in a lot of ways that the technicians get more of that in their education and in the field. But that's an argument that's long standing. I won't get into. And then there is a technologist. I haven't heard of that as much. But we had different levels and degrees of technicians where I spent most of my career, so I suspect it's talking about the difference between those types. So there is a fundamentals program that can qualify you, and I would think that would tend to be more on the technologist side than the pathway that we have with industrial, biomedical, or communications. And again, it's an unlimited field, and it covers a ton of items from communications, your cell phones, two-way radios, microwave, radar, and just a ton of things. And of course, the internet now is carried through a lot of those means as well. Computer systems, industrial systems, and biomedical systems. And we offer an industrial specialty, a biomedical, and a communications. We offer computers, but in a different area. Test equipment that you will use frequently as a technician is a digital multimeter. That is the heart and soul of what you'll use for troubleshooting in the field. Get to know it. I've got a very lengthy way for you to get to know multimeters in this course, and we have heard of cases where students skip over this. They don't put their heart and soul in it. We still have to tell them, as we're going through, we try to help, but maybe we hold hands a little too much at times. But if you can't turn on and operate a multimeter, you are going to be a very poor technician. And we've seen cases of that where people get out in the field and they can't even operate that, and it's crucial. Frequency counters, function generators, oscilloscopes, and those type things are some auxiliary equipment you'll be working with. This is just some of the different things. Upper left-hand corner is the digital multimeter. Can't really make out in the little small pictures there what those guys are, but at the top they look like maybe function generators and frequency counters by the fact they've got BNC connectors right here. Got an analog multimeter. You may see one of those, and you'll get to use some in the lab, and then an oscilloscope, and you'll find out what each and every one of those does. A circuit is something that performs a specific function. A simple circuit is a light switch and a light and a power source. So there's power to make the light come on. There's a switch that keeps the light from coming on until you close the switch, and so forth and so on. And part of your journey is going to be learning about all of these components, which there are many, many different types that have led to a revolution in digital electronics when you consider that a bag phone 30 years ago is the size of a shoebox, and now you carry not only a phone but a computer and everything else in your pocket. We have come a long way in a short time, and that's going to continue, I have a feeling. Resistors are one of the components. They limit current. Their value is ohms, and they also make something called a potentiometer. If you've ever turned a radio up and down or a TV up and down by turning a knob rather than pushing a button, you have operated a potentiometer. That is a variable resistor. That's just some of the examples of things that you see here. These are different types of resistors, and you can see pretty large, hefty resistors here, and these little surface mount resistors over here, and everything in between. Capacitors, they oppose a change in voltage. The unit is the farad, and they were also known as condensers. You'll hear old-time mechanics speak of a condenser on a car. That's just a capacitor. And that's what different ones of those look like. Inductors, they oppose a change in current. Their unit is henries. I'm not sure if I covered the capacitors or not, but their units are farads. And in our inductors, their units are henries. And they are coils of wire around some type of core. So transformers and things like that are a form of an inductor, as well as these things here, and a lot of these get used in the communication field to stop noise and to vary frequencies and things like that. Vacuum tubes, this is the old school stuff. This is what was around 70, 80 years ago. Not that long ago for some of you that remember cathode ray tubes, the old thick monitors and TVs we used to have before all the thin guys came along. They were vacuum tube, and that's some of the old-fashioned vacuum tubes. They had kind of a unique sound in the old vacuum radios and amps and things that used to be produced. Semiconductors, that's what replaced a vacuum tube. They did for several reasons. They're smaller, cheaper, more efficient, more rugged, and but they don't have the high power capability that vacuum tubes had. These are some that you'll see now. Integrated circuits, this is what helped revolutionize the industry. We were able to take, and rather than have a circuit that took 10, 12, 15 components or more to do something, we integrated that into one package, and it looks like this. And that's why you see all the different pins, because before this would have been a whole circuit that had different access points to it through the different components. Now it's all integrated. That's the name IC, or integrated circuit. We're going to look at printed circuit boards and some other units. My kids had one of these phones. This is one of those see-through phones. It's kind of neat to be able to see in and see the components. But you can see right there, there's some resistors, some capacitors, some transistors, and the like right there in front of your eyes. We used to make boards like this at Allen Bradley Rockwell that I worked at. And these are PCB boards. Most of what you see here is surface mount, meaning this board is double-sided. So we were able to, this is another thing that has made things smaller. If you look at this, this is what we call through hole. You can actually see the holes. The components were on one side, and the soldering and the path was on the other side that connected all of them. But now the components and the pathways, and that's what all these little lines that you see, are on the same side and can carry through to the other side of the board too, through different layers of the board. So that has revolutionized electronics. And that's just a typical schematic. Don't worry, this should look very confusing to you this early on, but as you go along, this will become a whole lot more clear. You can't just typically look at a schematic unless you've been doing this a long time and know exactly what it does, but you can start understanding what the different components, for example, this is what we call a bridge rectifier right here. This takes AC and converts it to DC. This is a transformer. This looks like an optical isolator here. So again, I don't know exactly what this circuit does, but I know a lot of what is in here and how it should operate, and I can get a good idea of maybe what's wrong. One of the things you're going to need to learn is scientific notation, and more specifically engineering notation. And engineering notation is a form of scientific, but we always use powers of 3, like 10 to the 3rd and 10 to the 6th and 10 to the 9th and 10 to the negative 3rd and 10 to the negative 6th and 10 to the negative 9th. So if you didn't pay attention in math, you'll go through some here. This is the time. And if you need to know how to use your calculator to do this scientific notation, there's all kind of helps that varies based on the calculator. We've got some tutors that can help you there as well. So if you have questions, please let us know. This is just more on that. And you got to be careful about order of operations. There's an old saying, please excuse my dear Aunt Sally, and that is PEMDAS. P for please, E for excuse, M for my D for division, deer, I mean, Aunt is addition and subtraction, Aunt Sally. So you can remember PEMDAS. That simply means that anything in parentheses is done first. So we would have to add that 2 and 3, and then multiplication or divisions next. So once we add that 2 and 3, we get 5. So 10 divided by 5 equals 2. But if we just go left to right, we're going to say 10 divided by 2 is 5 plus 3 equals 8. And wrong. So we have to make sure we get that right. So that's, please excuse my dear Aunt Sally, or PEMDAS. That's your engineering notation. You probably heard all of these. They may not have stuck with you. But kilobytes is what memory and RAM and all used to be 25 years ago. And you use that same prefix, that K, that lowercase k, in mileage on your car. Yeah, my car has 20K miles. That means 1,000. My car has 20,000 miles, 20K miles. Or I make 40K a year. That means I make 40,000 a year. And these are all multipliers greater than 1, and they're in powers of 3, 10 to the 3rd, 10 to the 6th, 10 to the 9th. The reason we use the lowercase k is before this system came along, we had already used the uppercase K for Kelvin, which is a temperature measurement. So all the things less than 1 are lowercase or Greek letters, but this is the only exception, at least on the most common ones. Now, we're getting in computers where we're going to have to bypass tera and go to the next, which I believe is peta. But anyway, it's going to grow, it's going to change. But kilo means times 1,000. Mega means times 1,000,000. So if you heard of the mega lottery, so talking about millions of dollars. Giga, you'll hear that with computers a lot. Gigabytes and terabytes. That means billion and trillion, respectively. So you would have to take and multiply 10 by itself 3 times to get 1,000, because 10 times 10 is 100, times 10 is 1,000. To get 1,000,000, you have to do that times 6. So we'll start at 1,000, which is 1/3. So 10 times to the 3rd times 10 would be 10,000, 100,000, 1,000,000, and it just keeps growing, pardon the pun, exponentially there. The inverse is true here. When we say milli, micro, nano, and pico, we're talking about fractions. We're talking about taking something and dividing it by 1,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000,000. And you'll see those prefixes here. So basically here we multiply times 10 times 10 times 10, or times 10 times 10 times 10 times 10 times 10 times 10. 10 to the 3rd, 10 to the 6th, 10 to the 9th. We would divide by 10. So obviously there would be 10 divided by 1 divided by 10 would be 1/10, 1 100th, 1 1,000. So we're literally dividing over and over by 10. Converting numbers to engineering notation, you'll play with that quite a bit once you get into the math section. But again, we take these numbers, and one of these slides once upon a time had an error. Let's see if it's this one or if they fixed it. 3.42 kilohertz. So the decimal place is right here. So we would convert that 1, 2, 3, and we would say 3.42 kilohertz rather than 3420 hertz. Let's see if this one's right. So this would be kilo, mega, tera, giga. I believe that is right. They have fixed the slide. Kilo, mega, giga, tera. Wait a minute. Kilo, mega, giga, tera. So decimal points here. If we move it this way, it'd be kilo, mega, giga. Yeah, it's still right. But if we had to move it one more, it'd be tera. So at one point they had that one confused. So just imagine, it's not hard to say 3,420 hertz, but it sounds more precise if we say 3.42 kilohertz. But it is pretty hard to say, hey, this thing's putting out 54,340,000,000 watts, but it's not hard to say 54.34 gigawatts. So that's where the difference lies. You need to understand the difference between precision and accuracy. The more precise a value, the more exact it is. And just bear in mind that precision and accuracy are not the same. A pitcher tosses the ball at exactly 93 feet per second. So the given is he really did lob it at 93 feet per second. This one got closer. It is more accurate. It got closer to the actual speed, which we said is actually 93 feet per second. So it read that value more accurately than all the others did. But it says here guns 3 and 4 are more precise. Now, I think guns 2 and 3 are more precise. Maybe this is the one that was faulty, not the one before it. Because there's more precision here. We've got more units here. We've got a higher degree of precision. So I think this is the slide that is incorrect. Let me find you a quick slide. I'm going to pause the video. This slide is something I'm more familiar with to tell you the difference between accuracy and precision. This guy's accurate. He stayed all around the center of the target by about the same amount. This one's precise. It stayed in the same general area. This one's both accurate and precise. In other words, we're clumped together. That makes the precision. The fact that we're hitting the target is accurate. And this is neither. So accuracy is an instrument's degree of veracity, how close the measurement comes to the actual or reference value. So if you go back to our slide, remember we had one that was very close. Precision is an instrument's degree of repeatability, how reliable it can produce the same measurement over and over and over. So I'm not exactly sure how they arrived at what they did in the other slide with it being an over and over thing. But anyway, you get the fundamental idea, but there is a difference between accuracy and precision. So you're going to be learning a lot in this journey, but you're going to need to ask some questions at times. Please do that. We're here to help you. And the one thing that I have gotten good at is knowing when students need help and don't ask for it. But the one thing I'm very bad at is reading minds, so I can't help you if I don't know what you need help with. So please reach out.